And now it's time for questions 14 through 19 on our final review. Excuse me, I just took a drink. Question 14. You'll notice, by the way, that my pages don't quite sync up to yours because I made the spaces wider so I'd have more room to write. I did not do that with you guys because I wanted to get less paper. Number 14. What section of the periodic table are the following elements in? Iron, manganese, gold, and silver. Well, here's my periodic table. Iron right here, manganese, cobalt, silver are all in this center section. Now, if you have the pretty periodic table, you'll notice that they're all colored in gray, and the name on that, on the key, is transition metals. So, they are all transition metals. They tend to form brightly colored compounds. They tend to be multivalent, meaning they have more than one ionic charge. So, there you have it. Name the major regions of the periodic table. First group, I'm not going to try to write sideways, so the alkali metals. For B, we have the alkaline earth. For C, we just answered that one, transition metals. For D, the green area here, those are the metalloids. They divide metals and nonmetals. This is the lovely stair-step line. The gray part here isn't labeled, but if it were, it would be labeled nonmetals. Plus the orange, and these guys are all nonmetals, and hydrogen's a nonmetal. These guys in here are not labeled. These would sometimes be called the poor metals. E are halogens. Oh my gosh, what'd I do? Sorry about that. E are the halogens. F are your noble gases. I think I spelled noble wrong. As a Nobel Peace Prize. G are your lanthanides. H are your actinides, so named after the first element in that series. We also refer to these as the rare earth elements. Number 16. An element is a member of Group 3A, and it is in period 4. Well, let's first review what does group mean. Group is up and down. This is Group 1, Group 2, Group 3, and it says period 4. The periods are those going across, those rows across. So here is element Group 3A, and here is period 1, 2, 3, 4. So we are talking about gallium. Named for France, because they used to call France Gaul. G-A-U-L. All right, which of the following has the largest atomic radius? Now, to understand atomic radii, which is simply the size of the electron cloud, we have to understand electronegativity. Electronegativity. Electronegativity talks about how attractive an element is. All right, I like to refer to that as people's sexiest man alive. For those that prefer the ladies, you can, Esquire has a sexiest lady alive. I believe Emilia Clarke has been it the last couple years. This is 2018, not 1918. Oh my gosh. 2018, she's the dragon lady from Game of Thrones. But this is how I try to get you guys to remember what we're talking about here when we talk about electronegativity. Okay, these guys all have an attraction. Okay, and when we talk about attractiveness, the most attractive element on the periodic table is fluorine. Fluorine has the highest electronegativity. So this is people's sexiest man, fluorine. All right. Now, why is that important? Well, if you're attractive, everything, all the other electrons want to be around you. Consequently, he's so attractive, he holds his electrons tight. So he has a very small radius. As we go this direction, you'll notice the radii get bigger till you get this far away. This is because there's only one, and there's not enough protons to really pull it in tight. Fluorine, this side of the periodic table has more protons than the left side, so they're going to hold it much tighter. Okay? You'll also notice the radius gets larger as we go down. That is because we add additional electron shells. As we go down, additional shells are added on, and they get bigger. So we have, they're further away, so that attraction lessens. Basically, if this is the sexiest man alive, this is the unsexiest man. This would be cesium, francium, even bigger. All right, so let's see if I can get rid of this. When we talk about that, the largest radius is going to be the element in the far right corner. All right, strontium is in the lower left, tin is in the right hand lower side, iodine is in the right hand lower side, silver is in the middle, barium is in the left on the left hand side. Let's bring that back just so we can see this. Strontium right here, barium right here, silver, iodine, and I don't even remember what the other one was now. Tin. Okay, who's going to have the biggest one? Barium. What do you do with the dead guy? Barium. That was for Jake Henson. All right. So, barium will have the largest atomic radius. Which of these are going to be the largest? Well, hydrogen, the first one, has 1 electron. If he has a negative charge, he's going to have 2 electrons. Electrons repel each other, so they're going to push each other apart, so he's actually going to get a little bit bigger. So it would actually be like this. If he's lost his electron, he's going to be even smaller and have a very tiny radius. So the largest is going to be the hydrogen with a negative charge. Now that should be a 1. I don't know why I wrote an I. The medium size then would be the normal hydrogen, and hydrogen with a +1 will be the smallest. Metals versus non-metals. Metals are shiny. They conduct electricity. They conduct heat. They make positive ions. Non-metals are brittle. They have low density. They may be gases. They do not conduct. They make negative ions. One more we can throw on metals is we can tell that they are malleable, which means they can be pounded into thin sheets, and they are ductile, which means they can be pulled into thin wires. How does the atomic radius change as you go across the periodic table? As you go left to right, it gets smaller. As you go down, it gets larger. Ionization energy is the energy it takes to remove an electron. Well, if you have a big radius, it's not going to take much energy to get that electron off. So a large radius equals a low ionization energy. A small radius is a high ionization energy. Thank you for attending this segment.